Hello, I'm Claudia Doram. I'm a professor of theoretical physics at Imperial College London. What I do is really try to understand the universe around us, everything around us, nature around us. I like to understand why the universe is the way it is at the moment, how it has evolved towards its current state, where it's headed towards. And one of the questions I'm particularly interested in at the moment is to understand what is making the universe and why the universe is behaving the way it is at the moment, and whether the laws of nature that we use to describe how the universe is evolving and what it's made out of are always the correct ones, or whether there's some sign of new physics to be explored. I think we know that gravity is what makes things fall to the surface of the Earth, but it's much more than that. Gravity is what was responsible for making the Earth and the solar system and the galaxy and the clusters of galaxies and the whole universe in the first place. If gravity wasn't present, there wouldn't be any clustering of elements. The universe wouldn't have evolved to the state it is today. Actually, if gravity wasn't present, the universe would be a very dense and very hot place where no life could ever exist. It would just be a plasma of fundamental particles. So gravity is really the law that made everything happen. It's the law that made the whole universe being able to evolve, to grow bigger, to grow cooler, to have structures and planets get formed. But it's also, and more fundamentally, the laws that describes the very nature of space and times themselves. So it's so fundamental in our understanding of everything that we really need to understand gravity to an extreme precision to be able to understand how the universe is evolving and how it has got to the state it is today. If we think of two objects, for instance, how the Earth feels the gravitational attraction from the Sun, in Einstein's theory of general relativity, we can think of the Sun creating curvature in space-time, and then the Earth is moving in that curvature. But still, in Einstein's theory of general relativity, associated with quantum field theory, we can think of it more at the fundamental level as a continuous exchange of virtual particles between the Earth and the Sun. And this continuous exchange between the two is really one way to think of the gravitational force. And that's very useful if you want to think of how different gravity could be, because you can ask whether this continuous exchange of fundamental particles, the graviton particles, whether they could be massive instead of being massless. And so at short distances, this wouldn't affect the way the Earth sees the gravity from the Sun and how the Earth orbits around the Sun. But if you want to think of how the universe on very large distances is behaving, then the mass of the fundamental graviton particle could have a fundamental implication. So we need to have alternatives. We need to have theories where we have small modifications of Einstein's theory of general relativity, so we can compare various alternatives, competitors, and see what nature decides to be described by. Nature will decide. We won't. We just provide different models, and then we let observations tell us which one is the best fit.